Hi friends, in this video let us see the first and foremost neural network, Culloh and Pitts model. So this is after this name comes after the scientist called Culloh is one name of the scientist and Pitt is the another name of scientist, and these two scientists have done research and finally they have given the first neuron model in 1943, and that model is called Culloh and Pitts model. And let us see what is this model tells us. First we need to see the architecture. So the architecture is like this. Let the input neurons are from x1, x2 and so on xn, n xn plus 1 xn plus 2 and so on xn plus m. That means the blue colored neurons are from 1 to n and the green colored neurons are from 1 to m. So there are n plus m neurons in the input layer, and y is the output layer, and they are straight away connected from directly connected to, I mean input neurons are directly connected to the output neuron. There is no hidden layer in this architecture. So similarly this is the connection. So the blue colored neurons are connected to the red colored output neuron by weight W, and green colored neurons are connected to output neuron Y by weights minus P. Okay, these are the weights for them. Let us see what are those things, and this is the output. So this is the overall architecture of Culloh and Pitts model. Let us see exactly, so what are the difference between the green color and blue colored neurons. And the input means, see, it allows 0 or 1, that is it is a binary activated. So all these input neurons are binary activated. That means you can give the value 0 or 1, that's all. You cannot give the values other than these two. So these are the binary activated neurons. So we can give only 0 or 1, either 0 or 1. So that in that way, this is the simplest neural network, simplest neuron model. So that's why they have designed like that. So they can take the input either 0 or 1, that's all. And yes, the weights which are having positive number are called excitatory weights, and the weights which are having negative number are called inhibitory weight. That means the information is passing from blue colored input neurons to red colored output neuron, and the information is passing in the reverse direction from green color to red color. That means the information is passing from y to x. In our general neural networks also, that means in our biological neural networks, the same thing happens. For example, if one sensor is there, sensor identifies something, sensor identifies, I mean the neurons nearer to the sensor identifies the sensing element and given to the brain, and that brain is giving one signal to those neurons which are nearer to the sensor, maybe removing the hand or anything. And so while it is taking the input from sensor and giving to the brain is taken as positive, and it is the taking the input from the brain is taken as negative. So this is the thing. So this is the basic model in an analogous to the biological model. So that's why there are positive weights and the negative weights. The positive weights are called excitatory weights, the negative weights are called inhibitory weights. So as you, this is the simple activation function. Y is equal to f of y in, which is equal to 1 if the value is 1 if y in is greater than or equal to theta, or 0 if y in is less than theta. So this is the basic activation function, okay, what we have already seen in the artificial neuron model. Okay, the same function has been used here in this. As we know, yin is the net input, or we can call it as induced local field, and theta is the threshold. So we need to give the threshold such that There is some rules to identify the threshold, and those things will be discussed here only. And the idea of giving the threshold, some, for example, if any problem has been given to you and you need to identify the threshold based on your problem and based on your inputs, number of inputs and also number of outputs. I mean number of inputs, maybe number of excitatory inputs and number of inhibitory inputs. So the theta is the threshold such that, I mean, you need to have the proper absolute inhibition. That means you should not get the negative value. I mean, you should not get only inhibitory. So definitely you should have absolute inhibitory. That means definitely you should have some positive value. So for that, what you need to do is theta should be set as greater than nw minus mp, where n is the number of excitatory weights and w is the weight of the excitatory weight, and m is the number of inhibitory weights, that means green color neurons, m number of inhibitory weights, and p is the weight of the inhibitory weight. So in this way, theta should be, of course, sum of these two. Okay, if we take minus p as weight of inhibitory, so sum of those two. So this is the main concept for choosing theta. So for example, if there is no inhibitory weight, how can we choose the theta? So theta can be chosen like that: kw less than or equal to theta less than k minus 1 into w, where k is the number of excitatory inputs. Okay, for example, if there is no minus p, the green color batch is not there, only blue color batch is there, how can we find the theta? So theta can be found like this: kw less than or equal to theta less than k minus 1 w, where k is the number of excitatory inputs. Okay, this is the main concept of Culloh and Pitts model. It's very simple model. So this one slide can explain everything. So this is the clear explanation of architecture. Let us see how can we find out these things? How can we use it actually? So for that, I have quoted one example. This is logic end function. How the logic end function is proved by using Culloh and Pitts model. First of all, we need to see the truth table. X1 is there, X2 is there. There are two inputs and one output. So I have taken only AND logic for two inputs and one output case. So if input X1 is 0, X2 is 0, then the Y should be 0. Input X1 is 0, X2 is 1, then also Y should be 0. Input X1 is 1, X2 is 0, then also Y is 0. Input X1 is 1, X2 is 1, Y is 1. So this is the basic AND logic function. So how this will be realized in our Culloh and Pitts model. The threshold taken here is 2. So you can easily see, actually that is up to you whether you need to take inhibitory weights or not. Okay, let me first go ahead with the diagram, I mean architecture, then you can understand. Yeah, output, as you know, y is equal to f of yn. Let us see. Yeah, these are the things, x1 and x2 are the inputs and y is this one. Here we have taken only the excitatory inputs. Actually we need to write 1 and 1 here. You can write whatever, that's up to you. Weights are in your hands and threshold is in your hands, but you need to get the final output, that's all. So here I have taken 1 and 1 here. So the maximum, for the fourth case, I need to get the output y as 1. So if I put weight for x1 as 1, x2 as 1, then input, the last case I am checking. So as x1 is 1 and x2 is also 1, 1 into 1 is equal to, for example, let me explain you clearly here only. Yeah, this value is 1, even this value is also 1. So I am checking the last one. So x1 value is 1 and x2 is also 1. So multiplication of these two, I am checking net input, or you can call it as induced local field. So here this value should be y in. So y in is equal to multiplication of these two, this one and this one, plus multiplication of these two. Okay, as you already if you can recollect the previous chapter, so you can have it. So multiplication of these two will come as 1, and multiplication of these two will come as 1. So finally it will be 2. So the output should be, my output should be, it has to be shown as 1. According to this, what I need to do, according to this f of now I need to write the activation function based on this case and based on other cases also. So the output is 2 here, and the y in is 2. If y in is 2, I need to get y as 1. So I need to write the activation function in that fashion only. So in this case, so as the y in is 2, I have taken 2 as the threshold. If the value is less than 2, make it 0 for all the cases. If the value equal to 2, make it 1. If the value is more than 2 also, make it 1. So which implies I can write my activation function. That will be shown in the next figure. You can see here. So yeah, this is the net input or induced local field. Y in is equal to sigma I is equal to 1 to 2. Here there are only two inputs, xi, wi. Xi is the input of ith neuron and wi is the weight of the ith neuron, what we have already seen in the previous slide. So y in is equal to x1 into 1 plus x2 into 1, as we have chosen weights w1 and w2 are 1 and 1. You can choose whatever you like. If you make it 2, your theta will be changed. Okay, that's very simple concept, so that's up to you. That's your convenience in which way you need to prove it. That's all. So finally my y in should be x1 plus x2, and for this formula I need to write the activation function. So my activation function is like this: y is equal to f of y in, it should be 1 if y in is greater than or equal to 2, it should be 0 if y in is less than 2. That's all, very simple concept. So based on this I need to check the entire truth table, and the output should be like this. See, this is the case 1, x1 equal to 0, x2 equal to 0. So the inputs are in green color, in the case 1 is in red color, and the final output is 0, that will be in blue color. So y in is equal to 0 into 1 plus 0 into 1, where 1 and 1 are the weights as we have already taken, which is equal to 0. This is my induced local field. This is my induced local field. Yeah, this part is my induced local field. And finally y is equal to f of y in, which is equal to 0. As why it is 0? Because according to the activation function, the induced local field is less than 2, so the value will be 0 here. In the same lines we can see the case 2 also. Same thing for case 2 also, the induced local field is 1, which is less than 2, so the value will be 0 as per the activation function. Similarly for case 3, here also the induced local field is 1, which is less than 2, so the final value will be 0. Very simple. So the final case is the value is 2, as this is equal to 2, so the value will be 1 as per activation function only. So your job is, you need to provide the weights and you need to provide the activation function to get the proper output as per the truth table. Okay, that's what we have to do it. So very simple neural network. This is Culloh-Pitts model. Very simple thing. Okay, based on this some other problems are also there, so I will do those problems also. They are very simple problems. I will do those problems also, and I will put in the video in the next video. Okay, so this is the concept of Culloh and Pitts model. This is the first and foremost the simple neural net model. After that so many models have come. This was done in 1943 by the great scientists Culloh and Pitts. Okay, thank you so much for careful listening, and if you like this video, please like it. If you want to share this video, please share with your friends. If you haven't subscribed to my YouTube channel, please do subscribe and kindly press the bell button so that you will get the notifications whenever I upload any video. Thank you so much.